Good morning, good afternoon, good evening. Welcome to Carl Academy. In today's lesson, we are going to cover set theory, and the lesson is divided into two parts. That is, the first part will covering the two objectives, that is terminologies related to sets, types of a set, and then set operation. And this will comprise part 1 of the lesson. Then part 2 will cover set properties, Venn diagram, and application areas of a set. Without much ado, please subscribe, like, comment, and share. Welcome. Before we proceed with sets, we have to understand what is a set. What is a set? Simply, what is a set? So we have to define a set. And a set is defined as a collection of objects. It's a collection of objects. However, it is a well-defined collection, meaning that there is no room for ambiguity. Then a well-defined collection of elements or objects. This means that a set contains elements, and sets are named and represented using a capital letter. For example, set A contains A, B, C, D. This means now that the set A has members, and these are the members of set A. These are the elements that comprises set A. That you say that in set theory, the elements that a set comprises can be of any kind: people, letters, numbers, shapes, variables, and so on. Let's look for another set. That is set B. 1, 2, 3, 4, 5. In set theory, the elements that a set comprises can be of any kind, that is people, letter of alphabet, numbers, shapes, and variables. That's why you can even have set C, which comprises of names, that it might be Carl, Alan, Alice. There might be a set of 3 employees of Carl Academy. Let's say an example. That's how we define set. So simply a collection of objects of element, and these elements must meet certain criteria. So in our next discussion, let's focus now on which criteria does a set must have so that to qualify to be a proper set. And then this part we are talking of a requirement of a set. That is that these are now the criteria that a set should meet. First of all, a set must be well defined. No room for ambiguity. There's no room for ambiguity. For example, a set of all students. This raises such a question such as which students? Why are these students? What is the time frame? I.e., when? A well-defined set should be a set of all female students pursuing ICT in colleges in Kenya in the year 2010. You have answered all the questions. There's no room for argument. There's no room for doubt or argument. Then the second part is a set must be distinct, meaning that the elements of a set must only appear once, or the object of a set must only appear once. There is no repetition. Seeing here 2 and 2. So the correct set A, as we take as an example, will be 1, 2, 4, 7. Another one is the order of presenting the elements of a set is immaterial. This means that it doesn't matter how you present them, in which order you're presenting them. However, and it's only that what matters is that the elements are not changing. It's only that you are changing. For example, 1, 3, 2, then 1, 2, 3. Only 1 is starting here, followed by 3, then followed by 2, then 1 is starting, followed by 2, followed by 3. So it's only that you are rearranging However, the elements are still the same. So those are the requirements of a set. Then in our next part now, we are going to cover representation of a set. How do we represent a set? There are three ways of representing a set. That is semantics. We are talking of describing using word. Simply using word to describe a set. For example, a set is the list of the first five odd. A set A. We're getting a set A is a list of the first five odd numbers. List of the first five odd numbers. So it just be written simply A first five odd numbers 1, 3, 5, 7, 9. First five odd numbers. Then a set of odd numbers less than 7. So it will be less than 7. It will be up to here. Odd numbers less than 7. So you present it using the words and then you close. So if this is the set, then you write there's odd numbers less than 7. You're just describing. That's what we call semantics, word descriptions. Then another way of representation of a set is the roster form. In roster form, we denote a set. For example, here you see that let n denote the set of 5 natural numbers. So you'll take that n must contain first 5 natural numbers. 4, 5. And this is, we call it a roster form. Like this one here, this is like a roster form. There's no words here, but in this one I'm using words. And these words we call them representing sets using semantics form. And this is another one is a roster form, whereby you are highlighting, you are giving the real elements of that set. Then there's another last part, that is set builder notation or set builder form. Set builder form. Here is that you take the set P, that's the set, then you equate it to set X, whereby now the X set, you have to meet the requirement now. That we say X is a counting number and greater than 12. A counting number is a counting number and greater than 12. Greater than 12. So you are using these two semicolon here, the way it has been used here, or you use this simple in set builder notation. So those are the three ways of representing a set. In this part now, we are going to cover types of a set. We have several types of a set. We shall cover as much as we can. So the first type of a set is empty set. This is called an empty set. Is an set without any element or without any object. Just a null set. Is an empty null. Then an empty set is represented using this symbol, or these are the two symbols that represent an empty set. For example, a set of apples in a basket of grapes is an example of an empty set because in a grapes basket there are no apples. A set of prime numbers. In a group of even numbers, something like that. Then the other part is singleton or a unit set. It only contains one element. Contain one element. Single one. Contain only one element. There is only one apple in the basket of grapes. So it means now that that basket contains only one element. That element is an apple. Then we have the finite set. These are a set that contain definite number, meaning that you can count the numbers. Definite number, you can count the numbers or the elements of that set. They are definite. You can know that they are 10, 50, 100. For example, set A contains 1 to 10. You can count there are 10 elements in this set A. Then we have infinite set, a set which is not infinite. You can't count. You cannot know when it will end. For example, a set A that contains 1, 2, 3, 4, 5, 6, 7, 9. Then the dot shows that the elements are not ending. So you don't know when they will end. E.g., this one also can be presented as 1, 2, 3. Then you put the dots. You don't know when they will end. Call that infinite set. Then the next type of a set we have is equivalent set. Equivalent set. Equivalent set. Equivalent set. Here, for you to get the difference, you have to apply just that if you have two different sets, then they are equivalent if the number of elements in each set are the same. In other terms, you can say the cardinality of the set are the same, meaning the value n here, this shows the number of elements in set A, and this is a number of elements in set B. You see that, for example, the set A contains 1, 2, 3, 4. These are 4 elements in set A. Then set B contains red, blue, green, black, a set of colors, a set of numbers, 1 to 4. So you'll find that the elements here are 4. Then the elements here are 4. So these elements equal. So we say that these elements are equivalent to each other. They are equivalent to each other. You have to be very keen to differentiate between equivalence and equal set. In equivalent, we are focused with number of elements. Are they equal? Number of elements. Yeah, we are focusing on number of elements. Then let's look at equal sets. In equal sets, the element must have same number of elements in the two sets, and then those two sets, the elements in those two sets must also be of the same type. In other terms, we say they are same elements. They must be of the same number and they are same elements. Meaning, for example, A 1, 2, 3, 4. Then B is 4, 3, 2, 1. These are the same elements. Here you know now the n of A is 4. Then n of B is 4. Then after that, you have again to confirm that are the elements the same? We have 1 cancels with 1, 2 with 2, 3 with 3, 4 with 4. So we call this equal sets. The order of element do not matter. The order of element do not matter. And we cover this one in the requirement of a set. We say that set order is immaterial, meaning that it's not important to factor in. So in this one, we say that now set A equals set B. And here in equivalent, we say n of A equals to n of B. Means that number of elements in B equals to number of elements in A. And this doesn't mean that the elements must be the same. No. When the elements are the same, then we call it equal set. When they're not the same, as you see here, B is for colors, then A is for numbers. We call that an equivalent set. I think you have grasped the concept. Then the other part is we are talking about disjoint sets. For example, you have two sets A and B. These sets are disjoint if they do not contain any element in common. They do not contain any element in common. See set A here. The elements in set A. The element in set A are 1, 2, 3, 4. In set B are 5, 6, 7, 8. So the elements in set A are not, or they even don't share any elements in set B. So these two sets, we call them disjoint set, because the element in one of the set, we shall see in Venn diagram, let's say A, and this one is B, they don't share anything, so they cannot form something like intersection. We shall cover in the next topic. So another part is a subset. Sub, then just a set, which means that a subset of a set is just a part of a specific set or equal to that set. We say now that let's use an example so you get it very well. Means that for B we call it a subset. This means that all elements in B are in A. That's why we call that A is a subset of B. That's why we call that B is a subset of A, meaning that all elements in B are also contained in A. So you see now A here. Let's say these are the elements in A. 1, 2, 3, 4, 5, 6. So now we say now that B is a subset of A, meaning that all elements of B are contained in A. All elements of B are contained in A. All elements of B are contained in A. So let's now do an example here. Let's take an example. Yeah, this is a good example I've done. Then you have to know that a set is a subset of itself. A set is a subset of itself. A set is a subset of itself. Then if A is not a subset of B, then it will be, for example, if B is not a subset of A, then we shall write that way and then we close that to show that B is not a subset of A. That means that B might be containing other numbers. Let's see so that you can be clear. Let's say B contains the elements here are 9, 1, 2, 3. So this one we shall call that B is not a subset of A. It's not a subset of A. And then here we are saying that B is a proper subset of A. It means that all elements of B are contained within the elements of A. That's why you'll see that now here 1, 2, 3. We shall cancel that 1, 2, 3. Cancel just 1, 2, 3. Yeah. Let's check again. Then let's talk of proper sets. We call them proper subset. A proper subset has to meet this criteria. That is, elements of A must be in B. If we are saying A is a subset of B, then another one now, A must not be equal to B. Yeah, A must not be equal to B. We call that a proper subset. For example, if A equals to, if A contains, if set A contains 257, then set B contains 257. Then this is not a proper subset. If A contains 25, if A contains 25 and subset and A is a subset of B, then this is a proper subset. Then we have this part. How do you know the number of subsets in a set? For example, here, let's confirm with set B. Set B 2, 5, 7. How many elements it has? It has 3 elements. For you to know the number of subset, it is 2. Yeah, it's 2 raised to, not 2 times n. It is 2 raised to n. 2 raised to n. So it will be 2 to n. Then you'll find that it will be 2 times 2 times 2, which is 8. Then let's confirm. Can we get all those sets? So we have 2 is a set of its own. Then we have 5, a subset. Have 7. Then we have 2, 5. Then we have 2, 7. Then we have 5, 7. 1, 2, 3, 4, 5, 6. Then shall have an empty set. Then we shall have the same set 2, 5, 7. That's how you get these are this 8, 1, 2. The empty set, let me put this way, 1, 2, 3, 4, 5, 6, 7, 8. So in that we'll get the 8 subset. Now let's look at the superset. A is said to be the superset of B if all elements of B are in element of A. So is that in simple terms as proper set, superset and opposite of a proper set. But however, it means that now the elements of A, all the elements of A, all the elements of A are contained in B. It means that A has enough elements compared to B. It is better to use an example so it can be easier. A and then B. So we say that A is a superset of B, meaning that it has more elements than B, and all elements in B are contained in A. That's why you have 1, 2, 3, then 1, 3, 4. 1, 2, 3, 4, then you have 1, 2, 3. So you're having an extra element here that make A super. So it means that in other terms is that B is a subset or proper set of A. Yeah, that's the opposite of superset. I need to get it clear. Then when you talk of universal set, these are all set relevance to a certain condition. We call them universal set, or all set elements under discussion. All set elements that are under discussion. So for example, if set A 1, 2, 3, then set B, then the universal set here will be 1, 2, you take just 1, you don't repeat. 3, you take 1, then 4, 5. So it will be 1, 2, 3, 4, 5. This is now the universal set represented by U. These are the symbols of the set. Then the other part we are seeing is the power of a set. Power of a set. A set of all subsets of set A including itself and null or empty. Those are what we call a power set. Is all the subsets including itself and the null. Yeah. So here, for example, let's work with an example for it to be okay. Set A. Subset of set A, we shall have a null 1, 2, 3, 1, 2, 3, 3, 1, 3, 1, 2, 3. There are 1, 2, 3, 4, 5, 6, 7, 8. So the subset of A, we have 8 subset. So now you shall say that now P of A equals to, you put down all, first one is empty, 1 2 3 1 2 2 3 1 3 1 2 3 1 2 3 4 1 2 3 4. This is empty. You put that an empty set. That's how you define a power set, all subset plus itself and the null. Then what's a Venn diagram? A Venn diagram. A Venn diagram. A Venn diagram is just a schematic representation of elements in a set. For example, this one, because it's a universal set. Then we shall have other sets like set A, element of set A. These are other sets within the, yes. So that's A, B, C. This is how now you shall discuss in the next operation, whereby shall be looking at when they intersect, how do we call them? Then they shall confirm more about it. That these are the sums. That's why it says that it's a diagram that shows all the possible logical relationship between an infinite assemblage of sets or group. So you can see that A, B, and C, how are they related? A and B. So it means that A has some elements in B, then A has some elements in C, then B has some elements in A, then B has some elements in C. Then what, you have another one here? It might be D. D has these unique elements. Yeah, that's how we shall be using the Venn diagram in our near future, where we shall be solving problems using Venn diagram. Then let's talk of set cardinality. It's just a measure of size. Set cardinality, we are just measuring the size, meaning that the number of elements, simply the number of elements. I talked it when we are starting. I show you the number of elements in a set. That's why I say written a set. So for this one, which has how many elements, let set R be 1 2 3 4 5. So that will be presented as R equals to 5, meaning this set R contains 5 elements, and these 5 elements contains are here. We have 1 2 3 4 5. Simply I would say that cardinality of a set is just elements in that set, simply elements in that set. So as we finalize this part 1, the first section, let's acquaint yourself with the symbols. They are very important, these symbols, to know, because when you say U, this means this union. U, then that's opposite of U is an intersection. Then this is a universal set. Belongs to meaning A belongs to A, meaning A, B, they all belong to A, meaning that A and B are elements, members of set A. Then A, B, they do not belong to A, meaning that A, B are not elements or members of A. Then proper set, yeah, can also be explained that this way. There's a proper set, still can be explained that way. Then we have this part, proper set. This one is a proper set. Proper set. That's how we play proper set. Then the next part is a subset. Is a subset. An element. A set that has elements that are contained in another set. That's the first element will be a subset of that element that has all the elements that contains in all the sets. Then not as a proper subset of, means that that element is not a proper subset. Let's say set A is not a proper subset of B, meaning that the elements in A are not contained in B, not a subset of or not contained here. Then C, complement. A, complement. These are now the elements that are not contained in A but are in the universal set. There's empty set. How to play an empty set. Then elements, number of elements in a set. These we're talking of cardinality. Cardinality. Then power of a set. Then we have this one shows the symmetry difference. We shall cover them in the future. So let's now talk of set operation. These occurs when we are combining two or more sets to form a single set under some of the given condition. Then in set operation we shall cover union of a set, then we shall cover intersection, then complement of a set, Cartesian product of a set, and then set difference. This is what we shall cover in set operation. Let's start with a union. In union we are confirming between two sets if they share some elements between the two sets. For example, here we have set A contains 1, 2, 3, then set B contains 4, 5, 6. These are two elements. Now, when you do the set operation, it means that now it will be A union B, meaning that this one will contain all the sets in A and B without repetition, so that shall have 1, 2, 3, 4, 5, 6. These are our new elements in that operation. That is a union operation. However, if let's say B could be also containing 2, 3, 4, 5, 6, we would not repeat 2 and 3. We should only take 1 because they are common elements, 2 and 3. So they'll be appearing here 2 and 3 once, not twice, because there are 2 and 3 here, and then in our new set B we have 2 and 3. So we don't repeat it. We don't take twice an element. So we don't repeat. That's why they must be distinct in one of the requirements of a set. They must be distinct. So here we shall have that the union of A and B, the union of A and B, the union of A and B will just remain that is 1, 2, 3, 4, 5, 6, 5, 6. So next, let's look for another operation, that is intersection operation. In intersection operation, we are doing an operation between two elements and come up with the elements that are common between the two sets. As you see here, if a set A and set B are two sets, then set A intersection B is a set that contains only the elements that are common between the two sets, denoted as A. This means that we shall only pick the elements that are contained in A, and the same elements are also contained in B. That's what then we shall pick. For example, these two sets, set A and set B, let's see which elements are common. There are no common elements here. So the only common element there is null. The element there that is common is null. So we shall pick null. These are the null, how to write null. Then let's do another example here. Let's assume that A contain 1, 2, 3, 4. Let's assume, and then B contains 4, 5, 6. You'll find that now in this one, there's a common element between the two. Common element. That's the factor here we are looking for, a common element. The common element here is 4. This is a common element. Now, our set operation will be A intersection B, which will be having an element 4. Are we together there? So if you have any query, please put the query in the comment, subscribe, share, and like. The next operation is complement of a set. Complement of a set, denoted as PC, or you can just say PI. For this is the set we have taken, a set of P. Yeah. So we say that a complement of P, let's say a complement of P, which will be P complement. These are all the elements in universal set that are not in P. All elements in universal set that are not in P. That are not in P. All elements in universal that are not in P. You see that P union P complement will get a universal set. Then P intersection P complement. P intersection P complement, you will get null, meaning there is no intersection. So let's use an example here that will be thus clear for you. Let's say universal set equals to 1, 2, 3, 4, 5. This is a universal set. Universal set. Then they say that P contains 2 and 5. So now P complement will be these are elements that are in the universal set that are not in P. It will be 1, 3, and 4. So the answer here will be P complement. P complement will be 1, 3, and 4. Then see this operation. Then the first one is P union P complement. So it's just simple as 1, 2, 3, 4, 5. Yeah. That's why I say P union P complement equals to universal set. Yeah. Yeah. So that is how then we are talking of loss of double complements, whereby you say that P complement and then you have another P complement, you get equals to P. So they cancel out the values of P. Yeah. Then let's look for the other part, and the operation that is set difference. Set difference is just elements are contained in one of the sets and not in the other set. That's very straightforward and direct. That you say this as A minus B, meaning that elements in A, you remove the elements in B, and then you get what is A. Just simply like when we have the A as 1, 2, 3 and B as 2, 3, 4, you take which elements can be removed by B, that is 2 and 3, because they are contained here 2 and 3 now. A minus B, will get it is 1. And that is the set difference between A and B. The set difference, simply as that. Then the other part is the Cartesian product. In Cartesian product, we are talking of a product of the two sets. That's a product of the two sets. Simply a product of the two sets. Just simply a product of the two sets. Yeah. So, for example, if you have or simply you can also say that it's just an ordered pair of a set. It's a set of all ordered pairs. So, for example, if you have A, the elements of A are A and B, and then the elements of B are, for example, 1, 2, and 3. 1, 2, and 3. Then A multiply B, product of B will be, first one is A1, that will be a first pair of set. Then the second one, A2, then A3, then B1, then B2, then B3. Simple as that. The same way as this one, you see. Set B, then set A, so it will be one ball and one bat, two ball, then three bat. Yeah, you are multiplying this one and this one, then you are then multiplying this one again, and this one, then you are multiplying this one. If the symbol, then you have 2 with this one, then 2 multiply with bat, then 3 multiply with bat, then 3 multiply with ball. Simply call that one Cartesian product of a set. Yeah, just multiply by A, multiply by that, by that. Then B multiply by that, and by that. Simple. Indicator, we call this a Cartesian product of a set. So we are finalizing the lesson. Now let's do some recap on what we have covered. Then we call it a day. So we have set notations. These are just, let's talk of set notations because the set notations will really help us. Let's start with this set notation here, whereby what is a set is a collection of elements. The way it has been presented here, just collection of elements. These sets, let's say it's a P or K sets, contain 1, 2, 3, 4 elements. Then was a union A and B or both, meaning that all the elements in A and B, that C and U contain all. The intersection in both A and B, the element that's only found in A and B. Simply because here this one is for D and this one is for C. Yeah, simply that one. Subset, every element of A is in B, so that's a subset. Every element a subset something. Then we are talking of proper subset. Every element A is in B but has more elements, but B has more elements, but they are not equal. That's why you say A is not equal to B. Yeah. Then not a subset, then not a subset. Then a superset, A is a superset of B. Yeah. Then A is a proper superset of B. A has B's element and more. A has B's elements and more. A is not a superset of B. That is how we do the recaps. Yeah, we do the recaps. Then superset. And then we talk of complement, open note in the universal. Then set difference you minus. Then A, elements of A as in E. So it means that elements on A has elements like A, 4, and other elements A, B, C. They all are elements of set A. Then B is an element. B is not an element of set A. So an empty set, universal set. Oh yeah, it's okay. Then power of a set, all subset of a set. Then equality, both set have same element. Quality, Cartesian product, set of ordered pair, you multiply. Cardinality, the number of elements in a set, shows us such that A is n, such that n is less than 0, is greater than 0. Yeah. So these are the examples. Like this one, 4, meaning 4. This one, the opposite, they exist. We shall learn this thing as we proceed. Then these are symbols for natural language. When you see n, natural languages 1, 2, 3, 0, or the integers, you have negative 0, 1, 2, 3. Then rational numbers that can be divisible, numbers that present in fraction forms, in ratios, algebraic the equations, real numbers, there are counting numbers, imaginary numbers like 3i, complex numbers like 2 plus 5i. Yeah. These are other set notation that we must know. These are other set notation that you must know. Thank you for watching. Please subscribe. Share, comment, like. Goodbye.